Welcome to Physiology 501. This lecture took place on August 20th of 2015. It was taught by Dr. Eltit. What I'm going to try to do is just highlight the important concepts, the confusing concepts, and I will just briefly go over the other stuff. So the first few slides will include things that you should be already familiar with. The plasma membrane, the phospholipid, the fluid mosaic model, some examples of the phospholipids that are in your membrane, and some are more concentrated on the outside leaflet and some are more concentrated on the inside leaflet. Phosphatidylinositol is going to become a very important phospholipid, and it's involved in signal transduction. Lipid rafts, you will learn a lot more about this in biochemistry in Mod 4. This slide, it's important because you have to be able to differentiate integral proteins from peripheral proteins. The integral proteins are proteins that can only be removed when you use a drastic measure, such as using a detergent. The peripheral membranes, these can be separated by milder methods, such as messing with the electrostatic interactions, hydrogen bonding, and then they'll come off. In this figure, you'll see that these two proteins are in peripheral proteins, whereas this is an integral. So is this one, and that one. This is a GPI anchored protein, farnesyl anchored protein, and myristoyl anchored protein. So these are integrals, integral, well, this one, and this is a peripheral, and so is that one. Homeostasis of body fluids. This is a really important concept. You have 3 different compartments when it comes to body water. You have intracellular fluid. This is inside your cell. And then you have extracellular fluid, which is outside the cell. And ECF can be separated into plasma, which is your blood, except the cellular components. And you have ISF, which is your interstitial fluid. So ISF, ECF, so plasma, ISF, these two are ECF, and then this will be your ICF, intracellular fluid. So if you use this concentration equals mass over volume formula, you can figure out what the volume is, because you have these tracer molecules that you can inject into a subject, and these tracer molecules will permeate throughout the compartment that they penetrate, and then you can, if you have the mass and volume, if you have the mass and concentration, which you can measure, you can figure out what the volume is going to be. So here are some examples. If you use heavy water, it's going to permeate all compartments. So you have total body water with heavy water. And if you have inulin, which is a kind of sugar, and this is going to come up again in renal chapter as well. If you have inulin, you can measure your ECF. So with this, we measured TBW, and with this one, we measure ECF. And if you subtract ECF from TBW, you get ICF, which is intracellular fluid. And you can also measure your ISF by measuring ECF and then plasma, and you subtract plasma from ECF, then you get ISF. Now you might be wondering, like, why do we have to subtract these two values in order to get ICF and ISF? And the reason for that is because you cannot directly measure ISF and ISF, because you can't have a tracer that only permeates your ICF. Therefore, you have to figure out what your ECF is and then subtract that from total body water. in order to figure out what your ISF is, you got to figure out what your ECF is, and then plasma, and then subtract plasma from ECF. Then you can get your ISF. If you want to memorize these values, the easiest way to do it is by remembering 60, 40, 20. So 60% of your total body weight is going to be your total body water. 40% of your entire body weight is going to be intracellular fluid, ICF. And then 20% of your total body weight is going to be your ECF. So 40 plus 20, you get your 60 back. And of that 20%, 3/4 of it is going to be your ISF, interstitial fluid, and then 1/4 of it is going to be your plasma. So if you have 70 kilograms, you can do the math: 60, 40, 20, 1/4, 3/4. Principle of macroscopic electroneutrality is a very important concept. This tells you that within different compartments, the sum of cations and anions have to be equal. So for example, cell within cell, so that's intracellular, 156, 156, ISF 150, 150, and plasma 152, 152. We had to memorize the concentrations for sodium, potassium, and I believe chloride on our exam. So sodium, you're going to find more of sodium outside than inside. Same goes for chloride, sodium chloride, that's salt. You'll find a lot more potassium inside the cell than outside the cell. And this is partially because of the sodium-potassium pump, the sodium-potassium ATPase. Calcium, you have very, very low concentrations of calcium inside the cell. It's in the nanomolar range, and you'll have a lot higher value in your extracellular compartment. So this is your ICF, and this is your ECF. ECF is split into ISF and plasma. Milliequivalent is millimolar. So this is your concentration multiplied by charge of the particle. So for sodium and potassium, it's just going to be 1. For calcium, it's going to be 2. And magnesium, it's again going to be 2. Some mechanisms of how solutes and solvents can move. They can move by different ways. Next slide. This is a really important concept. Flow and flux. So flow only tells you how much stuff is moving in absolute amount. So you can have high flow. That does not tell you whether you have a high flux or not. Flow, Q, is about the volume that's moving. The flux tells you per unit volume. So I can, for example, say I drove 5,000 miles. Well, over what kind of time period? So here, again, the same concept applies. You can have a large flow. Doesn't mean you had a high flux, because if you have a large area, then you can have a low flux but high flow. So let's see how this plays out. You're going to be seeing lots of units on this exam. I highly recommend that you memorize these. And once you understand the concept, you don't really have to spend effort to memorize these. If you understand the concept, the units will come with that. So Q, S is for solute. It's moles per second. Kind of makes sense. It's the amount of solute that's moving. So you're going to be using moles per second. As for the solvent, you're going to be using cubic centimeter per second. That's the volume that is moving. Now, as for JS, JS and JV, the flux, you got to take your flow and divide it by the area, because flux is concerned with per unit area. So if you do QS over A, you get moles per second times centimeters squared. And as for JV, which is the solvent's flux, again, flux is per unit area. It's really important. So you take your Q divided by A, then you get centimeter per second. And that's distance per second, which is equivalent to velocity. So now we're going to start using JV, which is flow of solvent, as just V, and that's velocity. So solvent can drag along solute, and the way we're going to figure out what JS is by taking JV, which is the flux of solvent, and multiply by concentration. So JV times C, and that's the same thing as VC, because we figured out that the solvent flux is equivalent to velocity, and velocity's unit is centimeter per second. So we do centimeter per second multiplied by concentration, then you get moles per second per centimeter squared, which is equivalent to this right here. Pretty cool, right? So to go from JV to JS, you multiply this value by concentration. And that's again because you can do concentration multiplied by volume is equal to mass. So that's how you can get your JS. Fick's first law of diffusion. I highly also suggest that you remember the names of these laws. So Fick's first law of diffusion tells you that the solute's flux is equal to negative D times delta C over delta X. D is your diffusion coefficient, and delta C is your concentration difference, and delta X is the lipid bilayer thickness. So if you look, this delta X is equal to 0 right here, and delta X is that thickness, right? So you have high concentration on the left side, low concentration on the right side. So you're going to have a net flow from left to right. On this figure, it's right to left. So it always goes along the concentration gradient. And that's the importance, that's the significance of this negative sign in JS. Always goes from high to low. And it will always go from high to low unless it's an active transport. Permeability. So we'll take this right here, Fick's first law of diffusion, and we're going to add some more variables to it. So negative D times K times delta C over delta X. Just to explain what this is showing, you'll take these three values and then write it as P, and that is your permeability. Permeability's unit is centimeter per second. So let's talk about these variables. D is the diffusion coefficient that we discussed on the previous slide. Your K is something called a partition coefficient, and what that means is when you have a solute and you're trying to dissolve it in some kind of mixture that has both an organic layer and an aqueous layer, it's going to dissolve in those two compartments in different ratios. So something can dissolve better in the organic layer, or something can dissolve better in the aqueous layer, aqueous being water layer, and then organic layer being the lipid layer. So in this equation, in this solution model right here, this is showing you that the higher the D, the higher the K, the lower the X, and higher delta C, you'll have higher JS. So if your diffusion coefficient is higher, higher JS. Higher partition coefficient, higher JS. So that makes sense, because if your solute likes to dissolve in the lipid layer more, it can just dissolve through the lipid layer and get across. And if your delta C is high, that means there's a high concentration difference, so you'll have high flux. And the dissolution model is just simple diffusion through the bilayer. The microporous model tells you what the flux of the solute is going to be when you have protein channels. So in this case, you have negative N over A multiplied by pi a squared times d times delta c over delta x. So let me break it down. Large N is the number of pores, number of available pores, and A is the area of the pores. So the area of the membrane, sorry. So if you have a lot of pores, but the area of the membrane is huge, then effectively you don't have as many pores per area. So you want a lot of pores in small area if you want your JS to be high. And then you have pi a squared, which is the area of the pore, and then D diffusion coefficient, and then delta C concentration difference, and delta X, it's again the lipid bilayer thickness. So if you have when you have this micropores model, you can take every single variable, including the negative sign in front, and rewrite that as P times delta C. So JS is always just permeability times concentration difference. If you look at this graph, your independent variable is delta C and your dependent variable is JS. And JS equals P times delta C is just like Y equals AX plus B when B is 0. So it's Y equals AX, and A is always the slope. So your P, your permeability, can be expressed as the slope of a line that shows you the relationship between JS and delta C. So the higher the delta C, the higher the JS. And if your permeability increases, that means the slope is steeper. Then for equivalent delta C, you'll have higher flux. Kind of makes sense. Questions, true, false. When delta C increases, JS also increases since the permeability is larger. Now this is going to be a false statement because when delta C increases, JS increases. That's true, but it's not because the permeability is larger. Delta C increasing has nothing to do with permeability because the permeability has to do with the diffusion coefficient, partition coefficient, and lipid thickness, lipid bilayer thickness. So the answer to this question is false. True or false? Increasing the amount of open channels in the membrane for a specific molecule increases the permeability for it. This is a true statement. If you open up more channels, you have increased your permeability. So let's see. What you're doing is you're increasing this number right here. So if that goes up, your P goes up. Therefore, you will have increased JS. So now it's starting to look like a physics lecture, and that's fine. You will find that on the first exam, there are a lot of equations and math-oriented questions. If you're good at physics, this is going to be a lot of fun for you. In this example, Q is your charge, and you have velocity V, and here's your electrical field. And this is the force that is produced on that charge by this field, and FD is the drag force. So when these two are equal and balanced, you reach terminal velocity. This FE is equal to Z times little e times big E. Z is your valence number of the valence on the particle. Little e is the charge of an electron, and big E is that electrical field, which is delta psi over delta X. And that's your gradient potential. So let's see how this is really used. We're going to talk about electrochemical potential. So mu is your free energy. We here are talking about the free energy on the left side and the right side. So mu R is equal to mu naught, which is the chemical potential of the substance under standard conditions of no potential, and these are the conditions you need to be in. Ultimately, it really doesn't have much importance because it's just the energy that's there all the time. What we're really interested in is the chemical potential and the electrical potential. So here's your chemical potential, RTLNC, and then your electrical potential, ZF delta psi. And you might remember from general chemistry that when your delta G is less than 0, the process is spontaneous because you have free energy. And if delta G is greater than 0, then the inverse process is spontaneous, meaning the reaction that's written is not spontaneous. And when delta G is 0, the system is in equilibrium. And this is going to be a very important concept. So here, if you hook up a battery to this lipid bilayer, then you can force these ions to go through. So this is the important slide: electrochemical equilibrium, Nernst equation, equilibrium potential. They're all the same. They have all same meaning. So we figured out what mu R and mu L are. They are the electrochemical potential of the right side and the left side. And we also wrote that at equilibrium, your delta G is going to be 0. So if we subtract L from R and assume that delta mu is 0, meaning the electrochemical potential free energy difference is 0, then we can figure out what the voltage needs to be in order to keep it at equilibrium, because here we assume that it's at equilibrium. And this Nernst equation, you gotta memorize it. If you see something in a box, you better memorize it. So negative RT over ZF times ln CR over CL. Just keep on repeating that. And CR, the right side, is going to be the inside. And the reason for that is because we're often interested in what's inside the cell, not outside the cell. So on the top, you're going to have the important value, which is the inside. And then outside goes here. So the Nernst equation tells you the energy required in volts. This is important. In volts, to keep constant a difference in concentration of a charged particle. So we're talking about ions. And we're talking about ions that have different concentrations on either side of the lipid bilayer. So this Nernst equation tells you, it gives you a voltage value you need in order to prevent a flow of the ions from one side to another. Well, the net flow is going to be 0 because that's what the definition of equilibrium is. So let's tackle a real problem, and I'll again re-explain the Nernst equation with this real example. So you have intracellular compartment, potassium inside, 35-fold, then outside, external, right? So again, Nernst equation, negative RT over ZF times ln of CI over CE. That ln of CI over CE is going to be 35. RT over ZF, these values are all going to be given to you. Z, because it's potassium, the valence charge, it's going to be just +1. So you do the math, and I suggest you do the math, not just read it or look at it, because on the real exam, you're going to get these numbers, and you might get units that are different. So I do highly suggest you do these problems yourself. You should also do the syllabus problems. It's really important. So you do negative RT over ZF times ln of 35, and you will see that the units you end up with is going to be joules per coulombs, and that's equivalent to volts. So you if you do all the algebra, you get negative 0.095, and that's equivalent to negative 95 volts. So what is the meaning of that? The meaning of that is if you have 35-fold concentration difference of potassium inside versus outside, you need negative 95 millivolts to prevent net flow of potassium. So remember, if the internal and external potassium concentrations change, then the equilibrium potential is also going to change. So let me use the previous slide to explain. So let's just assume that the inside, this side, is the 35-fold higher potassium concentration, and the left side is the outside. So if you have a lot more potassium inside than outside, what is the potassium going to want to do? It's going to want to leave. Well, if you have negative 95 millivolts, according to this calculation, you can have a JS of 0. You can keep it at 0 if your voltage is negative 95 millivolts inside. And that's what the Nernst potential tells you. It gives you the potential you need in order to keep the flux at 0 for given concentration ratio. And that's probably the single most important thing from this lecture. This concept, it's going to come up again and again. So it's important that you understand this before you move on. And please do the questions. You will have math questions, and people who like physics will do well on this first test. So good luck, and I will see you in lecture 2.